Hi, this is Andy Shaw from Black & Veatch. Welcome everyone to Webcast. That's kind of a primer to whet your appetite for the upcoming Energy and Water Conference that's going to be in Nashville from May the 6th through the 9th. I believe that's coinciding a little bit of overlap. It's the same venue as the Biosolids and Residuals Conference, so there should be some good interesting dialogue there. That particular conference is going to have 2 workshops and 14 technical sessions with topics going from anything from low energy treatment technologies to alternative energy sources, integrated planning for water, wastewater, and solid waste and electric utilities. If you want more information on that conference, please go to www.wef.org/energy to find out all the good details on that. So to get you in the mood for low energy, the low energy topic, we've got 3 interesting presentations from 2 distinguished speakers. I'll introduce each of the speakers, and then in between the 2 speakers we'll have a bit of a Q&A session. The questions for this webinar, if you could post them in the via text on the questions box that should have popped up on your GoToWebinar control panel, and then I'll select some of those questions and ask them of the speakers. So we'll do it individually, and then at the end there'll be some time left over. We can have a more general Q&A if there's particular questions that have not been answered yet. So without further ado, I'll introduce our first speaker. It's Dr. Leif Rieger, who's the CEO of In Control Solutions Incorporated. He specializes in monitoring, control, and modeling of biological wastewater treatment processes. Leif is the chairman of the IWA task group on good modeling practice, and I serve with Leif on that group, so I know him very well. I know he's a very capable modeler and expert on instrumentation and control. The focus of that particular group was to make modeling more practical for industries and consultants. Leif's an elected member of the management committees of the IWA specialist groups on instrumentation, control, and automation, and also on modeling and integrated assessment. So he draws those 2 things together in his discussion today. He's also a member of WEF subcommittee on modeling, the MEGA group, and the Automation and Information Technology Committee. And then he was chair of 2 seminars on wastewater treatment at the WWT Mod conferences. In addition to that, in his spare time, he's editor of Water Science and Technology, and he's associate editor of the Water Quality Research Journal of Canada. Reviews for several journals, and is definitely an expert in the field. So with that, Leif, I'll hand it over to you.
Thanks, Andy, for this nice introduction. Today I would like...
Sorry to interrupt. This is Rebecca. If you just click the orange arrow on your control panel, that'll move it out of the way.
Oh. Thanks.
There you go.
Okay, thanks. Today I would like to talk about ammonia-based aeration control. So everyone of you will know dissolved oxygen aeration control, and this is probably the next step in getting to a more efficient aeration control system. I would like to acknowledge some people. So the slides and the study, the case study I will show, involved quite a number of people. I would like to highlight the people from the Hampton Roads Sanitation District, Charles Bott and Bill Balzer. And I did this case study when I was still with Envirosim. Okay, so short overview. I will start with some context information about the benefits you can gain from introducing this advanced control. And then I jump into aeration control, and I would like to start with some nitrification fundamentals, discuss different ways of aeration control, and discuss a bit more on control fundamentals like feedback and feed-forward concepts, etc. And then I show a case study. This was a simulation study we did for the HRSD plant Nansemond. and then, of course, some conclusions. This is the graph probably most of you have already seen. This is from a web study, and it shows how much energy is consumed by what in a typical wastewater treatment plant. And you can see that the big chart part of this pie chart in yellow, the aeration is about 50%. So the range is varying, of course, but I would say about 40 to 60% of the total energy goes into aeration. So quite a bit of energy goes into your aeration, and therefore it's certainly a good idea to have a closer look into how to make it more efficient. Okay, so this is from some simulation and also full-scale implementation studies I did in Switzerland. And what I would like to focus on first is the first line, the energy. And what you can see there is that we simulated, and also in the full-scale implementation, we reached energy savings of, let's say, about 15 to 25%. So in the simulation, we predicted a saving potential of about 30%. And in the full-scale implementation, you see that there's less. So in the first plant in Morgenthau, we had about 20%, and in Thunersee about 16.5%. This is really full-scale measured. The reason was not that we had a bad model, but rather that there were a lot of plant constraints. So we couldn't really reduce the aeration enough to reach this full potential. This was partly related to turn down limits of the blowers. So we couldn't turn down the air enough. And the second plant, Thunersee, also had issues with mixing. So we were not allowed to go down with aeration because of mixing issues. So this shows that there's quite some potential. So even without using the full potential, we reached around 20%. So this is certainly quite some saving you can reach. The second line is about total nitrogen removal. This is probably something you didn't hear, or it's not often discussed. We will hear more about what's behind from Jose in the second part of this webcast. But what I would like to highlight is the fact that just by changing from a DO control strategy to a ammonia-based aeration control strategy, we saved full-scale, we increased denitrification and therefore total nitrogen removal by 40%. So there's quite some potential to even improve your effluent quality. The last line is about saving potentials. In the first plant, this was a 3.5 MGD plant. We reached about $50,000 per year, so every single year in total net savings. So this already includes the investment for sensors and maintenance, etc. So this is already quite some money for rather small plant. And you can see the larger the plants, the bigger the savings you can reach. So in Thunersee, it was about $360,000 every year. And the last one, this was only a simulation study. We predicted savings or saving potential of over $1 million every year. In this slide, this is about this case study I will present later. And again, so we were able to reach quite some energy savings, as you can see here, depending on the temperature. In blue, 12 degrees, red is 20 degrees, and then green is 30 degrees. And yeah, the saving potential in terms of energy, the highest at 30 degrees went up to $90,000 per year. What was interesting in this plant, it's a 5-stage plant with methanol dosage, and we didn't touch the actual dosage control. We just introduced ammonia control and provided more room for denitrification. And what you can see is that at 30 degrees, the saving potential was between $300,000 and $350,000 per year at 30 degrees. So quite some saving potential. And even at 12 degrees, where you would say, well, you probably need the whole volume for nitrification, you can see that there was still a saving potential of around $50,000. So quite some potential here just from introducing relatively simple and cheap control measures. So let's have a look into why we can achieve these savings. And what you see in this slide is that there's quite some variation in terms of flow and also in concentration. What is not shown in this graph is temperature, of course. But what this means is that wastewater treatment plants are really highly dynamic systems. And using control really allows us to run these systems more efficiently. So let's have a closer look at it. So as you have seen in the previous slide, we have this very high variability of the incoming load and the temperature. However, we typically deal with fixed reactor volumes. So you have fixed volumes for unaerated and aerated zones. And then we design these plants based on peak loads. This is something we have to, because of course we would like to be able to deal with whatever is coming in, right? All this together means that, well, we have, per definition, we have unused capacities, right? Because we design for peak loads and we have these variations, and this means that if the plant is not overloaded, every single day there should be potential to do something more efficient. Okay, so what we discuss in the next slides is really biological nutrient removal plants. And as you will know, nitrification is really the rate limiting step, and therefore should also be the target or the primary target of the aeration control strategy. Because of this, I would like to go more into nitrification fundamentals. So what is really required to run nitrification under optimal conditions? Of course, we need sufficient provision of dissolved oxygen. We need ammonia as a substrate and some essential nutrients. This kind of sounds trivial, I guess, but just I would like to make clear that if ammonia is gone, there's no nitrification. So it's not required, and therefore we also don't have to rate if ammonia is gone or is below a certain set point. What we also need is an aerobic sludge retention time, so that this is sufficiently long. And in the end, what we need is a sufficient mass of nitrifiers. And this is quite important. I will come back to this. So this is a key feature if you would like to design your aeration control system. What is shown here is the dependency of the nitrification rate, so how fast nitrification goes on, and the DO concentration. And there are two parts to it. In the lower DO range, let's say between 0 and 1.5 milligram per liter, there's quite a steep slope. This means if you lower the DO concentration, you heavily reduce the nitrification rate. So this is a nice control handle you can have. So reducing is quite easy and quite a powerful control handle. The other side is if you go higher than 1.5, 2 milligram per liter, there's not a lot happening. So rating more, having higher DO concentrations, is not improving the nitrification rate. And this is quite important, and I will come back to this figure a couple of times, and also I know that Jose will also show this slide again. So this is quite a key aspect here. So if we look at some profiles, the upper graph, this is an ammonia profile. The first tank, this is anaerobic. Then you have the internal recycle coming in, some dilution. So ammonia drops down. And then aeration starts. This is a plug flow reactor. And you see that ammonia goes down. And then in the fourth section, ammonia is nearly gone. So in the last two sections of this plug flow tank, there's no ammonia. So you could say, well, we don't really have to aerate here. In the lower graph, we see the oxygen uptake rate. And it's clear, I think, that in red, this is the oxygen uptake rate linked to nitrification. And of course, this goes down here. And at the end, you see just a minimal oxygen uptake rate. What you see is that there's still some oxygen uptake rate, or total uptake rate, but this is mainly related to endogenous respiration. This is clearly not something you would like to support. So you could easily switch off aeration. Okay, so what we looked into in the previous slide was just one point in time. So if we go on a time scale, what is shown here is ammonia. In red, this is the end of the aeration tank, and in blue, this is the ammonia in the secondary effluent. So most of the time, ammonia is 0, but once a day, there's a breakthrough of ammonia in the effluent. And I can assure you that every tank had a DO concentration of 2, so certainly enough oxygen. The sludge retention time, just the aerobic one, was 8 days, so sufficiently long. And altogether, the effluent concentration of ammonia is about 0.5 milligram per liter. So we will probably call this a fully nitrifying plant, right? So, but what is the reason for these peaks then? The reason is that the mass of nitrifiers is changing slowly and also depends on the average ammonia load and the sludge retention time. So the sludge retention time was sufficiently high. So in this case, it's only linked to the average ammonia load you removed. So on the other side, we have quite a high variation. Of course, this is an example. There was quite a variation in the influent ammonia load, and this varies substantially over day. So you have this variation, and you have an average nitrifier mass. This means that ammonia breakthrough often is due to the limited mass of nitrifiers and not at all linked to insufficient oxygen. And this is quite important to understand or to properly design your aeration control system. Sometimes you cannot do something with just increasing aeration, right? So it's not linked to oxygen. Often it's really linked to the mass of nitrifiers, and you have to come up with the control strategy dealing with this. Okay, so let's have a look into different ways of controlling your aeration, and the focus really is on ammonia-based aeration control. In fact, there are two different control goals or control objectives here, and it's quite important to distinguish the two to make sure that you come up with the right control strategy. The first one is limiting aeration. The goal is to reduce energy, increase denitrification, improve BioP performance, so really optimizing the efficiency of your plant. The second goal is to reduce effluent ammonia peaks. So it's not about efficiency, it's really to reduce the extent of the effluent ammonia peaks. If we look at the first option, the limiting aeration, the first thing I would like to discuss is what's really the difference between DO and ammonia control? And in fact, the DO control is to provide optimal conditions in terms of dissolved oxygen for all aerobic processes. So this is nitrification, but also for organic matter removal. Ammonia control, so if you introduce an ammonia sensor and do ammonia control, this is really to optimize nitrification. And the reason is that nitrification is the rate limiting step in typical municipal wastewater treatment plants. So as soon as you fully nitrify or nitrify down to a low set point, the organic matter is gone as well. So you don't care about organic matter, you focus on nitrification, but this is sufficient for most plants and mainly for municipal wastewater treatment plants. Okay, so how can we implement this ammonia-based control? And my favorite solution is that you have a cascaded ammonia DO control. And what you see here is that you have a DO control loop. So you measure DO somewhere at the beginning of your tank or in the first third of the tank, of the rated zone. You have a DO controller. You have a DO set point somewhere around 2 milligrams per liter. And then you calculate the manipulated variables. So you open or close a valve, let's say. Now we can measure ammonia. I would do it at the end of the rated tank. Measure ammonia. It goes into an ammonia controller. And the ammonia controller calculates a new set point for the DO controller. So the ammonia controller really sits on top of the DO controller. What you can do is you can vary the intensity. So change the DO set point between a certain range, from 0 to 2 or from 0.5 to 2, or you do intermittent aeration where you switch on and off. Another way of implementing ammonia-based control or aeration control is that you only measure ammonia. This goes into a controller, and the ammonia controller directly calculates the valve position. I am not that favor of this solution, and I will discuss why. So this is bringing back this graph I showed before. And what this means is as soon as ammonia is high, this controller will increase aeration. So if you have very high ammonia concentrations or a peak of ammonia coming in, this automatically leads to over-aeration. Of course, you could add another DO probe. What you would do then is just changing the setup. It's also cascaded aeration control, but then the DO controller sits on top of the ammonia controller. The reason that I don't prefer this solution is that it's more difficult to tune, and it also has some other practical limitations. So I clearly favor the first option. Okay, so now we go to the second control objective. This is reducing ammonia effluent peaks. And there are also two different ways of doing it. The first one is intensity control. So what we do is you measure ammonia or the ammonia load somewhere early on, and you get a fast information, oh, there's a peak coming in, let's say. And then you increase aeration to the maximum. So you try to provide optimal conditions for nitrification. You try to drive down ammonia in the tanks. And then you create a kind of a buffer for the incoming peak. So you dilute the incoming peak with low ammonia concentrations in your tank. The problem, again, is that the impact of this intensity control is quite limited because more aeration, so higher than 2 milligrams per liter DO, is not providing more nitrification. Another option to do this type of control is volume control. And what you actually do is that you change the rated volume by switching on or off swing zones. And what you do with this is really that you increase the mass of nitrifiers, of active nitrifiers. So this is quite a powerful solution, and in the case study you will see some more results. Okay, so now some control fundamentals. And this is mainly about feedback and feed-forward control and what are the differences. So I start with the most simple one. This is the feedback control. And this is really what you should use if you can. So what you have is a target variable, or in control theory you would call it a controlled variable. And then you define a set point. So, and of course the goal is to maintain the target variable or controlled variable around specified set point. Then you have the process and some disturbances. In our case, the process, this is your reactor or your reactors. And then you have disturbances, and this is the change in the influent load, change in temperature, change in operational settings, everything changing the process behavior. To control this, what you do is you measure the controlled variable, and the measured variable goes back, is compared with the set point. You calculate an error out of it, and this error is used in the controller. The controller will then calculate a control action, and then hopefully this control action has an impact on the process and is able to deal with the disturbances. So to remember, feedback control is really measuring the process answer. You don't have to know what's going on inside your tanks. You measure the answer, what's coming out, and then you change the settings of your control handle. The opposite is feed-forward control. And as you can see, the lower part is exactly the same. The difference is that now, instead of measuring the controlled variable, you measure the disturbances. And the other difference is that because you don't know what's really happening in your tanks, you also need a model of your system. And this is quite an important fact. If you now discuss advantages and disadvantages, the big advantage is that feed-forward control provides really fast reaction. And this is a reaction even before the disturbance hits the plant. So if you need to deal with fast processes, if you have peaks coming in where you have to react fast, then feed-forward control is certainly the way to go. The downside is that you need a process model. And a model is a simplification of reality. You need sensors as input or signals as input. And this means that there's quite a risk involved, right? So you don't know what's going on. You just predict what you think goes on. So there is a risk. So in my opinion, if you do feed-forward, it should always be complemented by a feedback signal. It could be that you combine feed-forward control with feedback control, or at least you should use the feedback signal, so the process answer, to tune your model, to make sure that your model is always right. Okay, so this is a graph, a scheme where we combined feedback and feed-forward control. You know the black part in the middle, the DO controller. The ammonia controller is also something I showed already. So it sits on top of the DO controller, calculates the new DO set point. But what is new is the green part. So you measure the flow and the ammonia concentration, so the incoming load. And then the feed-forward controller maybe compares the incoming load with the predicted nitrification capacity. So what the model inside thinks is the nitrification capacity, and maybe decides to also increase aeration. That the two controllers are not fighting against each other. We have put in a maximum criteria. So this is deciding which controller is going through. And we use the maximum criteria. This is pretty simple. The controller with higher air demands is going through. And this concept is also used in the case study, or was also tested in the case study. This last slide, this is also a cascaded ammonia DO controller. And what I would like to demonstrate with this slide is that there are a lot of control loops involved. So you have the ammonia controller, a DO controller, an airflow controller maybe. Then you have the airflow system, and inside there is maybe a pressure controlled aeration system where the pressure defines how much air is provided by the blowers and so on. And all these control loops are connected. This is mainly to make you aware that it's not a simple task to tune all these, because all have different time constants and have to be carefully tuned. So if you design your aeration control system, make sure that in the end you have a experienced control engineer doing the fine-tuning on site. So this is not something you can do in a model. There has to be somewhere going out and tuning. And often you need some retuning after a while, or just make sure that your controllers are properly tuned. Okay, so this was about fundamentals. Now we have a look into this case study I mentioned earlier. So this case study was about the Nansemond plant. This is one of the Hampton Road Sanitation District plants. It's a 5-stage plant, 60,000 cubic meter per day, 16 MGD, or about 250,000 connected population equivalents. What we did is we did a careful data evaluation, and we came up with 1 week of a typical pattern. So we had weekly variations, but also diurnal variations. And we came up with 3 different influence and temperature scenarios, and then 1 scenario where we created an artificial ammonia peak. This was mainly to test the feed-forward concept, and if we really need to implement this feed-forward concept. We tested a whole bunch of different ammonia-based control scenarios. First, we focused on modeling the existing control strategy, just DO control. Then we had a couple of ammonia feedback controls, and then feed-forward feedback ammonia control. If you're interested, just drop me an email. I can send you 2 papers from last WebTech where all the details about the control strategies are included. Okay, so what you see here is the plant has 3 independent aeration zones with DO set points 2.5, 2, and 1 milligram per liter. And the first step really was to model this existing strategy. What I would like to discuss in these slides is really the importance of the right DO sensor location. What you can see here is we modeled the control loops, and the control loops work perfectly fine. This is the model. It's simplified. In reality, you wouldn't see more noise on the DO concentration, but for this task, it's sufficiently accurate and yeah. So what you see here is that the control loops work fine. However, this is just where the DO probe is located. So if we look at the whole DO profile, and we spent quite some time also modeling the air distribution system, you can see that a lot of sections of these tanks have quite a high DO concentration. So this is the waste of energy. In this tank here, so it goes up to nearly 5 milligram per liter. However, even more important is that downstream of the second aeration zone, so downstream of the DO sensor, we realized that we have quite some low DO concentrations. This is not something you typically see because you don't have a DO probe in there, but it shows that the location of the DO sensor is quite important. So in this case, 0.5 means that nitrification is quite limited here. So what we did is that we moved the DO probes of the aeration zone 1 and 2 just a couple of meters downstream. And what I would like to show is just look at the red line here. In the top graph, this was the original setup. And the ammonia in the effluent has peaks going up to a bit over 1 at times. Then we moved the DO probe. So again, we didn't touch the control system. We just moved the probe. And as you can see, the peaks dropped by half. Right? So this is not related to the control. It's only related to the location of your DO probes. So if you use these dynamic simulators and you model the air distribution, you can get quite some nice information out of that. Okay, so the next slides mainly focus on testing the feed-forward part. Again, if you're interested in the whole study, just send me an email. I can send you the WebTech paper. So what we did is we modeled all the tanks, methanol dosage, all the recycles, and so on. And then, of course, we also modeled the 3 different aeration zones. What you can see here is that we already moved the DO probe. So first it was in this tank, in the first aerated tank, and then down we also moved the DO probe over the next aeration grid. Then we introduced an ammonia probe at the end of the rated section with the ammonia PID controller. In this case, we also introduced a feed-forward controller. So we measured the flow and the ammonia concentration in the first anoxic zone. The reason that we placed the probe there is just because of maintenance. Right, so it's much easier to maintain a sensor in the anoxic zone than running it in the raw wastewater. So again, you have this ammonia feedback loop, the ammonia feed-forward control, and then you have to have a selector, and the selector defines the DO set point for all the 3 DO control loops. Okay, so let's have a look at some results. So this is the oxygen concentration at the 3 different temperatures, 12 degrees, 20 degrees, 30 degrees. And you have to know that if the feed-forward part is active, it increases aeration to 2.5 milligram DO per liter. So as soon as you see 2.5 here, you know that the feed-forward part is active. And what you can see here is that the feed-forward control is only active at 12 degrees. So it's not active at higher temperatures. So the question really is, does it make sense to have such a complex system and it's only running for a couple of days? If we look at the results, so the ammonia concentration, this is at the end of the aerated zone. You also see that there's not a big difference between pure feedback ammonia control and the combination of feed-forward and feedback. So in black, these black dots here, this is the pure feedback, and in red, this is the combination of feed-forward and feedback. And I would say that there's no significant impact on the effluent ammonia concentration. So it works. We saw from the DO profile time series that it was active, but in fact the control authority or the impact really on nitrification is minor. The same is true when we use the last influence scenario with this big ammonia peak in the influent. And again, you can see in blue, this is just feedback. In blue, the dotted line, this is when you also have feed forward. And you see, again, even at extreme peaks, there's quite a limited impact of this feed forward concept. So to summarize, feed forward control, and this is only for limiting aeration, right? So you have to be aware that we only change the intensity of the aeration. In general, feedback control is more robust, and feed forward requires safety factors against model failures. A simple model may not be accurate enough. However, if you go for a more complex model, then you need several inputs, what means you need to buy sensors, maintain sensors, and this, of course, eats into your savings. The effluent ammonia concentration changes quite slowly. So I would say in most cases, a feedback control is sufficient. And as we could see, the control authority, so the impact of this control is very limited at higher ammonia concentrations. So to summarize, you have an increased risk. It's more complex, more expensive. It eats into your savings. It's often not required and sometimes not even functional. Okay, so this was about limiting aeration. So maybe you remember we had two options. The second option is volume control. So this is switching on or off swing zones. And by switching on a swing zone, you actually increase the mass of nitrifier. What is actually the limiting factor here? And if we look at this graph, you see again the black curve is the feedback part only. The red is feed forward intensity control, and in blue this is really the feed forward volume control combined with feedback. This is at the end of the aeration zone. If you look at the effluent, you can see the blue line really shows a nice straight line. So this is perfect control behavior. It demonstrates that the control of authority of volume control is much higher than intensity control. So if you have to deal with these peaks, you should go for volume control. Okay, so there are other issues coming out of these simulations. Now, I would like to focus on three different things. The first one is the minimum and maximum blower capacity. In this case, we didn't put the bounds directly in the model because we wanted to see if there is a benefit if we buy a new blower with a lower capacity and that we can run at lower airflows. What you can see here is that at this plant, there's more than enough blower capacity, but there is an issue with turn down capacity, and this is pretty typical. Normally in the design, you just focus on the maximum blower capacity, but it also means that you limit the turn down capacity. And in this case, it's clear that you cannot turn down enough. So as soon as you go into ammonia-based aeration control, you have to be aware of the limits in the lower region. So make sure that you include ammonia-based control already in the design phase and make sure that you can turn down your blower sufficiently. Another issue is mixing requirements. So what we did here is we just plotted the airflow, and this is just a literature value here for the minimum mixing requirements per tank. This is something, so the settlability of the sludge is really changing from plant to plant. So what I would suggest is that you test settlability and test how much air you really need to keep the sludge in suspension. And this number coming out with some safety factors, of course, this is what you put into your control strategy to make sure that you always have sufficient mixing. Or maybe out of the simulation study, you realize that it's actually cheaper to go for mechanical mixing. This is something I saw at a lot of plants, that we couldn't turn down the air because of mixing requirements. And this is something you nicely get out of these simulations. The last point is airflow per diffuser. My understanding is if you always run lower than the minimum airflow per diffuser, or from the specification of your diffusers, you might end up with increased fouling. So I recently had a discussion with a diffuser manufacturer, and they said no, they improved the material and it's not a problem. But well, I just say be careful in the design. If you always run lower than the minimum specifications, you might end up with increased fouling, and this reduces your efficiency of your aeration system, and then this is reducing your savings. And this also comes out of, or you get nice indications from your simulation study. Okay, so I come to my conclusions. I would like to remind you that ammonia-based aeration control really has two objectives. One is limiting aeration to prevent complete nitrification. This is really to optimize the efficiency of your plant. And the second one is to reduce ammonia effluent peaks. And be careful, you have to define these objectives up front, and depending on what is more important, you will come up with different control strategies. Limiting aeration is about saving energy. It improves denitrification. We saw more robust BioP. At Nansemond, we saw less carbon addition. And what is important to remember is that there's quite a high control authority for the impact of the control to limit nitrification. So if you reduce the DO level, there's quite a nice control handle you have. However, on the other side, just increasing DO levels is not improving nitrification. One thing you have to be aware of is the DO probe only gives just one point in your reactor. So it might be that you have to increase the DO set point to make sure that you have sufficient DO everywhere. The second objective is to reduce ammonia effluent peaks. And you have to remember that ammonia effluent peaks often are due to limited mass of nitrifiers. And this is really a kinetic constraint and cannot be solved by more air. So you have a very low control authority of aeration intensity control. And if you have to deal with ammonia peaks, then swing zones is really the way to go. So if you design ammonia-based aeration control, you have to ask yourself, what is really the control objective? And then is feed-forward really necessary? In my experience, most of the ammonia peaks you see are homemade. Often this is related to dosing the digester supernatant into the reject water in one shot. So you create a big ammonia-rich peak. Or it's related to not having the sufficient DO levels throughout the tanks, and so on. So you should solve these operational problems before you go for feed-forward control. Feed-forward aeration control often involves higher risks. It's more complex, it's more expensive, it eats into your savings, and at least if you go for intensity control, it has quite limited control authority. If you have to deal with effluent ammonia peaks, maybe you have industrial discharges and you really see these peaks coming in and you have to deal with it, then the way to go is swing zones or volume control. The last statement I would like to make is we have these nice tools available, and these dynamic simulators are really the perfect tool to also design your process control system and test it for various scenarios. Okay, so that's my presentation, and I'm happy to answer your questions. Thanks.
Andy, you might need to unmute your phone.
I guess Andy is gone.
Oh, sorry, my phone just dropped off just at the worst possible minute, but I'm back now. Thanks, Leifus, for a very good talk. It's provoked quite a few questions, so I'll select a few of them to read out. The first couple of questions are related to the example you showed of the Swiss plants.
Mm-hmm.
First question is, with your aeration energy cost, when was that done? And particularly, the question is related to, more modern blowers are more efficient, and therefore you would see different savings if you were using more modern equipment. So could you comment on that?
Yeah, so this was the reason that I provided relative numbers there. What I did, there were existing plants, and mainly the first plant had huge issues with overcapacity of the blowers. So what they did is they changed the diffusers from coarse bubble to fine bubble, and suddenly they were much more efficient than before. What ended up with one blower out of 4 running at the minimum, and still at night you were running into saturation. And we were able, just by using control, I didn't discuss it, but in this case, what we did when the load was really low, we even went into intermittent aeration. So we stopped the blower completely for about 20 to 30 minutes without any additional mixing, and then re-aerated. And this intermittent aeration made sure that we were not running into saturation. So this is really dealing with plant constraints, and the challenge we had was to deal with it only by control. And okay. If you see the savings coming out, that's quite something. On the other side, yeah, you have to mention that the kilowatt hour in Switzerland is, of course, quite expensive. Yeah. So it was about 15 cents.
Okay, so
but still, the relative number is still valid.
Okay. There was another question, I think you may have answered it in your response there. They were asking what capital costs were involved to achieve those energy savings in Switzerland. But it sounds like it was all control equipment. It wasn't major capital.
Yeah, so it's depending on the SCADA system you have. If you have a modern SCADA system, the implementation is extremely easy, right? It's just another PI or PID controller or on-off controller on top of the existing DO controller. So What is nice is that you use the existing DO controller and just add one. Main cost was related to the sensors. So you had to put more sensors in, ammonia sensors. And it's not the investment what is expensive. It's really the maintenance and quality control of the sensors. And this is quite essential because you drive the plant to the limits. So it's essential to have a proper QA, QC procedure in place. And this was most of the money we had to spend.
Okay. Actually, that's a good segue to the several folks have asked about recommendation on the brand or type of ammonia sensor to use. Do you have any guidance on that?
I would say that these ion-sensitive electrodes, they are ready to go. You have to be a bit careful with these sensors. You have to have proper QA, QC. So you should really do a grab sample and measure it in the lab once a week. Right, so you have to make sure that the sensors are properly maintained. You just have to compare so that the cheaper solution in terms of maintenance, spare parts is certainly the ion-sensitive electrodes. However, also these XC2 analyzers are pretty good. And I would go for a gas-sensitive analyzer then. There are a couple out there. The problem is that you need a filtration system, and this is quite some work you have to do. So what you do is you shift from maintenance into quality control. So in the end, you have to see how good your instrumentation people are. The XC2 sensors have advantages in terms of auto-calibration and so on. So you really have to see what's best for your plant.
Okay, cool. Good answer. There were a couple of questions on using control approaches that will lead to low DO environment. Mm-hmm. Would that impact settleability, or in the extreme cause bulking sludge? Would you like to comment on that?
Yeah, no, that's a nice question. So I had a slide in there, but because of time, I took it out. Actually, we followed settleability. So we had a couple of SBI measurements, but also followed in terms of the microbiology. So we did quite a series of tests and these fish tests, and we couldn't see any problem there. So to be honest, we had better results in the controlled, ammonia-controlled train than in the reference train. So we had less bulking. I also did a literature study and tried to find cases where there was a link between ammonia control leading to low DO concentrations at time and increased foaming or bulking. And there was really nothing I could find. I know that there are studies where DO is always low, but I didn't find anything showing a direct link between bulking and ammonia control. So in fact, in our plant, it was better than before. And this is also, I discussed with a number of people, and I couldn't get my hands on any plant where this caused any issues. But I'm happy to, if somebody has something, I would be happy to receive some results. Okay. I'm quite interested in.
Well, we've still got a pile of questions, but I'm probably just going to ask two more before we move over to Jose. There's questions on the swing zone, in particular. How does that, physically? How do you move? How do you use that? So one question is on, okay, would you have one zone that's not in use, or when you come back into using it as an aerobic zone, how do you resuspend the solids, and that kind of practical aspect of.
Yeah, typically this is under normal load conditions, this would be a denitrification zone, and then you would turn this into an aerated zone. So you most of the time you would have mechanical mixing plus membrane aerators at the bottom. But again, so this is an option. I would say this is only something for plants seeing this big ammonia peaks. It's quite difficult if you don't aerate for, let's say, 3/4 of a year, and then suddenly you would like to have full efficiency. That's difficult for the equipment. In terms of control, it's relatively easy. The only thing you have to do is that you have to make sure that this probably feed forward control for the swing zones is properly tuned together with the feedback ammonia controller. So
Okay.
not that it's too tough going in and out.
Yeah. Yes. Well, I apologize we can't cover every question now. Maybe if we've got time at the end, we can come back to more. But I'll just ask. There's one more here that intrigued me was the control approach that we're talking about is dealing with the highly variable nature of the influent.
Mm-hmm.
Could you achieve a similar benefit by having influent equalization?
Yes, you can, but it's more expensive. Influent equalization is probably more powerful, I have to admit, but it's more expensive.
Okay, excellent. Well, thank you, Leif, for excellent presentation, both from the theoretical and some practical ideas, and also the modeling, the case study. We'll come back for more Q&A at the end if we have some time, but I'd like to give Jose some time now to do his presentations.
Mm-hmm.
Thanks, Leif.
Thanks.
Okay, so Jose, Leif gave a nice presentation on ammonia-based aeration control. We've actually got two presentations from Dr. Jose Jimenez. He's going to talk about effluent removal under low DO conditions, so that's very similar kind of topic to Leif's presentation. But then he's also going to give a presentation on high-rate activated sludge system for carbon removal and the implications for energy from doing that. Give a brief introduction to Jose. He's a senior process and technical specialist at Brown and Caldwell. He's been involved with the functional design of numerous wastewater treatment plants across the U.S. His technical interest and expertise include nutrient removal and recovery for both municipal and industrial wastewater treatment. He does full plant modeling and model development. He looks at high-rate aerobic and anaerobic systems and renewable energy generation in wastewater treatment applications. Dr. Jimenez has worked as a senior process design engineer, carried out on-site research, authored numerous papers that have been published in peer-reviewed technical journals and several articles in national and international conferences. Dr. Jimenez currently serves as Brown and Caldwell's Eastern Regional Process Manager. So with that, Jose, I'll pass it over to you.
Thanks, Andy. And I'm hoping that you can see my screen now. And today my topic, I'll be talking about two specific topics. The first one is going to be efficient nutrient removal under low DO conditions, and that's a good segue from live presentation. And we'll be talking a little bit more about that. My overview today is going to be pretty simple. The outline is presented on this slide. We're going to be talking about nitrogen removal. What do we know about SND, or simultaneous nitrification, denitrification? Then we're going to cover some of the factors actually affecting SND for the removal of nitrogen. From those, I selected availability of carbon, dissolved oxygen concentrations, and sludge bulking. Then we're going to talk about applicability and implications of doing these SND type processes in existing or new facilities. And then, of course, at the end, we're going to try to talk about conclusions. First of all, we know that the biological reduction of nitrogen in the active air sludge process relies primarily on two mechanisms. One is aerobic nitrification, and then the anoxic denitrification. generally in conventional systems, in conventional DNR processes, these two processes are carried out in physically separated anoxic and aerobic zones with sometimes internal mixed liquor recycles. However, when we talked about SND or simultaneous nitrification, denitrification, we're actually now talking about the biological process where nitrification and denitrification occurs at the same time in the same reactor or within the same flock. And of course, we already had some questions about sludge bulking. We're going to talk a little bit more about that later. But we have to realize that by promoting SND in some of the reactors, we do encourage, really promote the conditions for low DO bulking, which is one of the disadvantages of this process. SND relies on achieving a dynamic balance between nitrification and denitrification. Since we're doing everything within the same reactor or within the same flock, we need to try to find what it works for one process and without affecting the other. And there are a couple of variabilities or processes that affect SND, and they're listed on this slide. First of all, we have the presence of microscopic anoxic or oxic zones within a sludge flock. We know that aeration promotes the dissolution of oxygen into the water. The dissolved oxygen subsequently diffuses into a flock, and along the diffusion path, it's consumed by the organisms. The diffusion and consumption of this DO causes a gradient of dissolved oxygen inside the flock, and at suitable low DO concentrations, it creates actually flux denitrified in the oxic outer layers, as we have in this figure here, and denitrified in the inner anoxic layers. So as you can see, we can select SND by selecting the proper bulk DO concentration and diffusion within the flock. Also, we have the presence of microscopic anoxic or oxic zones within the bioreactor. Such zones are commonly formed as a result of non-homogeneous mixing and aeration patterns in reactors. One good example that we can use to look at macro environments within a reactor is the conventional oxidation ditches. So, where we actually have two different layers. One layer, it's the top layer closer to the mechanical aerators where you have high DO concentrations. And then as you move further from that mechanical aerator and you move vertically into the reactor, you start getting to these anoxic zones where you can denitrify it. Then, of course, I already mentioned about the bulk DO concentration, and we're going to show some slides later on that will talk a little bit about that. And then carbon availability. We know we need carbon to denitrify it. So that's one of the main aspects of the SND to work properly, and I'll be talking a little bit about that. And also about the presence of novel microorganisms. We're not going to be talking much about it during these presentations, but we know that now we're all looking at about anomox and how anomox could be incorporated in mainstream plants, and this is one that could be used for a coupled with an SND reactor to facilitate the removal of nitrogen. Based on information that I've gathered in the literature, there are many advantages and disadvantages at the same time on SND, and here where I'm just selected a few of those. If we look at in terms of potential advantages for an SND reactor, we can eliminate separate tanks and internal recycles for denitrification, which will make our design and the operation simpler with some regards. Therefore, it's a simpler process design. But most importantly, when we looked at SND, simultaneous nitrification, denitrification, we're looking at the advantage of reducing the carbon, the oxygen and energy, and alkalinity consumption in a plant. To me, that's the main driving mechanism to move into SND or to move to some alternative pathways of nutrient removal. However, when you look at these advantages, here I'm listing a few that I selected from the literature and from my experience. And one is the limited control that the operators or the process engineers have on flock sizes, internal storage of COD, and DO profile within the flock. After we design a plant, right now there's not much we can do to select from those specific, let's say, the aspects of SND to optimize it. Then, of course, we have the sludge bulking. The propensity for sludge bulking due to the excessive growth of low-DO filaments have been associated as one of the main disadvantages for SND systems. I've known a lot of plants that they used to perform SND successfully in terms of nitrogen removal, but they had to move away from SND to a more conventional pathway of nitrogen just because of the horrible low-DO bulking conditions they were having, therefore affecting its capacity. And there's one that it caught my attention after reviewing the literature, and it talks about complex instrumentation. And I personally don't believe that this is actually a big deal now, especially after sitting and listening live talking about ammonia-based DO control or ammonia-based aeration control. And of course, the nice thing is that we can couple these SND reactions with what Live was talking about, ammonia-based aeration control. So I don't think that in terms of instrumentation, it's a big deal right now. Here we have the traditional approach to biological nutrient removal that we know that involves, and this is a little bit of the basics about the nitrogen removal. We know that we have the conversion of ammonia to nitrite and subsequently to nitrate by the autotrophic nitrifiers, followed by the reduction of nitrate to nitrogen gas by the heterotrophic denitrification. This is just a conventional nitrification, denitrification pathway. Nitrification, we know that it's an aerobic process. We need DO, as Live mentioned in his presentation. And we know that ammonia and nitrite function as electron donor during the nitrification process. Therefore, we have to have ammonia, we have to have nitrite to do a complete nitrification. In the case of denitrification, we know that the nitrate in this case that it was created during the nitrification process acts as an electron acceptor in the absence of oxygen, and it converts it to nitrogen gas. It is well known that if we couple nitrification and denitrification in a single reactor, we can reduce the net process oxygen requirement because now we're using the nitrate produced during the nitrification and subsequently use the terminal electron acceptor for the removal of the biodegradable substrate pretty much. So denitrification will allow us to reduce the actual overall oxygen requirement in this process. However, if we look a little bit deeper into that, we have that nitrification of influent ammonia results in the consumption of about 4.57 milligrams per liter of ammonia nitrified. However, the nitrate produced during the nitrification process can be used as an electron acceptor for the removal of biodegradable organic carbon, and it will result in an overall oxygen gain of approximately 2.86 milligrams per liter of denitrified. This will leave us, therefore, with an approximate net oxygen consumption of 1.71 milligrams per liter of milligrams of oxygen per milligrams of nitrogen removed, which is the net oxygen demand during nitrification, denitrification, similar to what we can get in an SND reactor. However, now I'm going to step a little bit further. I'm going to talk about what we've been calling recently about nitritation, denitritation. When we talked about nitritation, denitritation, we're actually referring to the nitrogen removal process in which the second step of nitrification, which is the oxidation of nitrite to nitrate, is inhibited. And then complete denitritation from nitrite to nitrogen gas can be achieved with some carbon. Nitrogen removal via nitritation, denitritation may yield up to about 25% reduction in aeration and 40% reduction in COD requirements, in addition of reducing the biomass production. These reductions in SND requirements would be particularly advantageous in wastewater treatment plants treating wastewater deficiency in COD. Therefore, we have some advantages in terms of doing this type of processes. This alternative nitrogen removal process has led to believe that some oxygen savings, as mentioned previously, we're talking about 25% oxygen reduction, could be realized, and therefore we could translate that to mainstream processes. However, if we step a little bit further about looking at these oxygen demands or oxygen requirements, we have that the net oxygen consumption results from nitrification. The nitrification is 1.71 milligrams of oxygen per milligrams of nitrogen removed. Actually, the same factor that we obtain when we looked at the conventional nitrification and denitrification pathways. Therefore, there's always the question about should we go and try to implement nitrification, denitrification, or just doing conventional simultaneous nitrification, denitrification, it's the right way to go. And of course, the answer is not straightforward. However, the selection at the end of the day, it's going to depend, based on my opinion, on your carbon to nitrogen ratio that you have in the wastewater. Now I'm going to talk a little bit about some of the factors affecting S&D, and could be S&D via nitrate or just nitrification, denitrification. We can call it S&D via nitrite. These two figures show the effect of the influence COD to nitrogen ratio or the BOD to nitrogen ratio on denitrification from a full-scale facility as well from a pilot plant. Data from the full scale, it's on the it's your left plot based on influence COD to TKN ratio. This data actually shows that complete denitrification can be achieved consistently when the influence BOD to TKN ratio is at least 6. However, when this ratio falls below 2, limited denitrification was achieved at the facility, since we have limitations of the carbon. Similar observations were obtained at the pilot plant, which is the plot on the right, where denitrification performance increased as the influence COD to nitrogen ratio increased. Very limited denitrification was actually observed at the pilot plant at low COD to N ratios, pretty much as low as 6 or lower. And there is not a direct comparison, since one plot is based on COD, the other one it's based on BOD. However, we can see that in both plots that we can actually achieve complete denitrification at high BOD or high COD to nitrogen ratios, which is pretty much showing the effect of that fraction on your overall nitrogen performance or your denitrification. Another factor that I want to touch on a little bit here is the control of DO or its effect on S&D. As Leif mentioned, that DO is critical for nitrification, and actually in most of the cases it limits the nitrification reaction, especially at these low concentrations. So we know that the control of the bulk DO concentration in S&D reactors is essential part for achieving the high degree of S&D. The success of the S&D process actually relies on the balance of the bulk DO concentration from both the kinetic reactions of nitrification and denitrification, and of course they need to happen concurrently in the same reactor or in the same flock. Based on the data that we presented here, this is from a full-scale facility, we can see that the optimum bulk DO concentration actually ranges from this facility specifically from about 0.3 milligrams per liter to about 0.7 milligrams per liter. When the bulk DO concentration, as shown in this figure, drops below 0.3 milligrams per liter, the S&D performance is limited by nitrification. Now we have lost nitrification, and therefore we get spikes of ammonia concentrations in the effluent. However, and in the other case, if the DO concentration is in excess of 0.7 milligrams per liter, now we are running with issue with denitrification in this case. It should be noted that these bulk DO levels are dependent on the flux size in the system. Therefore, it's difficult to draw general conclusions with this data about what's the best DO concentration for S&D. We know that the larger the flux might be, it might require higher bulk DO concentrations than the smaller flux. So overall, there's not much conclusions we can draw from this plot, but all we can say is that there's a sweet spot within your reactor where you can get nitrification and denitrification happen concurrently at the same time with the same DO concentrations, and you need to optimize it to that regard. We already saw this plot and it was presented by Live as well. And of course, this figure shows the theoretical effect of the bulk DO concentration on nitrification kinetics. For the purpose of this plot, we know that we're using a half saturation DO constant of 0.5 milligrams per liter that is presented on the figure. And as Live mentioned, we normally operate these facilities, these nitrification facilities, in DOs between 2 and 3 milligrams per liter. And the only reason why we do that is because, as we can see from here, we're maximizing the kinetics of nitrification. However, one can see that from this same figure that if we start dropping the DO to lower concentrations, especially from 0.5 milligrams per liter or less, similar to the results I presented previously, a significant drop in nitrification efficiency is going to occur and will eventually affect the performance of the plant. However, one nice thing about SND, and it's that actually we have two plots here, is that, for example, if you concentrate right now on the top right-hand plot, we have 3 bars presented in that figure. The first bar actually measures nitrification rates, or specific nitrification rates from a reactor operating at 0.3 milligram, at 3 milligrams per liter DO concentration. The DO was actually subsequently dropped to about 0.5 milligrams per liter. The reactor was spiked with ammonia, and we measured nitrification rate. And we observed a significant reduction on the actual nitrification performance of the reactor. We can see that overall the nitrification rate dropped from about 6 milligrams of ammonia per gram of VSS per hour to about 3. So it's approximately 50% reduction, or yeah, it's about 100% reduction. Yeah. However, after that same batch reactor was continuously operated at low DO concentrations, approximately 0.5 milligrams per liter. After 2 days of operation, we actually saw the nitrification coming back, even at the low DO concentrations, up to the point that we actually achieved 85% of the maximum nitrification rate from the reactor, as you can see in the bar chart. One of the reasons why this is important, because it seems there's some adaptation happening of the nitrifiers, both AOB and NOBs, to actually work at the lower DO concentrations. The same observations were actually obtained by Giraldo, and we have a plot in the bottom left corner of the slide, where he found half saturation constant for nitrifiers with really low numbers in the 0.01 milligrams per liter, which means that the nitrifiers not only can work at the high DO concentrations, but also they can operate fairly efficient at the lower DO concentrations. Now, of course, after looking at these different aspects of SND and looking at the new work that actually is currently being done in, for example, Blue Plains, DC Waters, Blue Plains, and also in Hampton Roads Sanitation District, now we have new tools that are being developed by these 2 research groups that actually will allow us to not only to promote SND in reactors, but also to optimize and to control these systems. One of the aspects that we're looking at right now is implementing ammonia-based aeration control, as presented by Live in the previous presentation, that will allow us a stringent control over DO to do nitrification, which means we will provide enough air to just nitrify what we have to. Then, of course, subsequently, we can control the aerobic SRT to as long or short as we need to by controlling the aeration profile. Based on some observations, especially on Hampton Roads and also on DC Water, this cyclical air, or this transient anoxia, as we're calling it, actually it's providing some benefits in terms of NOB repression. As I mentioned at the beginning, when we looked at SND, we have 2 ways of actually analyzing SND. One is via nitrate, which is complete nitrification and then denitrification, and the other one is nitritation, denitritation. In the cases where we want to implement the nitritation, denitritation, the key for doing that is actually NOB repression. So we will have to dig a little bit more into this if we want to maximize its performance. Here, I'm actually going to show a couple of examples of some continuous flow experiments and some batch experiments from two reactors. One operated at a constant low DO concentration of 0.5 milligrams per liter. Here we have the time series showing the F1 nitrogen species from that batch reactor. We started with the infant concentration was 25 milligrams per liter of ammonia. So as we can see in this reactor, we can, by using SND and by controlling the DO to really low levels or to low levels, we can actually drive the SND process, and we can drive the effluent concentration to the reactor with really low concentrations. In this case, we're talking about less than 5 milligrams per liter without any addition of carbon. I must say that the carbon or the COD to nitrogen ratio for this experiment was 10. And then also we collected samples from the same continuous flow experiments, and we ran some batch tests just to follow the profile of the ammonia over time. And here we have the results. What's interesting is that in this case, of course, we're not seeing much of the nitrite being built during the batch test reactor. We just saw a little bit of the nitrite being built as the reactor was started, but otherwise was consumed. Therefore, based on these results and a constant DO concentration, we could not inhibit the NOBs. Therefore, we didn't do nitritation, denitritation, but we did straight simultaneous nitrification, denitrification. The same reactor was then tried to be controlled using cyclical air, pretty much trying to control that ammonia or that effluent ammonia concentration to about 0.5 milligrams per liter. And then by actually switching the DO or the air on and off, we actually created this plot and from the results of the continuous flow experiment. Now in this case, one thing that we can see is now the nitrite concentrations from this plot is a little bit higher than the ammonia concentration from this plot, which means that the NOBs are actually slower than the AOBs, and therefore they have some nitrite left over from the process. We don't have complete inhibition of the NOBs, but it was at least significant to see some of the nitrate being shown in the effluent. And then if we compare this total nitrogen concentration, or at least the nitrates concentration with the previous plot, we can see that by doing this, we were able to reduce the effluent NOx by about 1 milligram per liter more than just continuous flow experiments. A similar batch test was performed using the seed from this reactor, and now, of course, now you can see a nice buildup of the nitrite during this process, which actually is an indication that the NOBs are being inhibited, or at least they've been suppressed during the process. The only difference between the two reactors was the actual cyclical air in the second reactor. Therefore, we think that by controlling that cyclical air and by providing some transient anoxia conditions, the NOBs can be inhibited, and then nitritation, denitritation could be implemented in mainstream plants. Based on the results from these experiments, we can conclude the following. We know that the AOBs, or the ammonia oxidizing bacteria, the rates of the ammonia oxidizing bacteria are not significantly affected during the SND. And the reason it seems because of some adaptation of the biomass to the low DO conditions. The nitrite oxidizing bacteria seems not to be inhibited by the low DO conditions during the SND, which means that it's really difficult to operate just a constant low DO reactor and then inhibit the NOBs. Therefore, by doing that, by controlling a constant low reactor, most likely we're going to select for simultaneous nitrification and denitrification. The NOB rates is slowed down during cyclical air due to the transient anoxia, well, at least that's the hypothesis we have. And therefore, we're creating a possible nitrate shunt during the process, where we're utilizing the nitrite from the nitritation as an electron acceptor for denitritation, therefore reducing the carbon requirements for this type of process. These are two examples of two facilities that actually were doing conventional nitrification, denitrification with high DO, and then they decided to try the SND mode, and just wanted to present here to show some of the savings for doing so. I want to concentrate here mainly on the Aeration flow rate, and in this case, they're doing some partial ammonia-based control for the SND. So even though I'm showing a DO concentration of 0.45 milligrams per liter, it actually varies, but that's the average of the operating conditions. If we concentrate on the airflow rate, we were able, by doing SND in this facility, reduce the airflow rate from about 9,000 SCFM to 6,100 SCFM, which is approximately 32% reduction in aeration demand or aeration requirements. In addition, we were able to reduce the acetate addition, the external carbon addition, from about 780 to about 300, which is a 62% reduction in carbon addition. That was the reason why the facility wanted to try SND rather than conventional. However, as we can see in the SBI, we did increase the SBI slightly, not much, but it was 25% increase. And of course, the effluent concentrations were all within the requirements for the plant. The second example I want to show here shows it's a similar facility. This used an AO process, and they did the same. They wanted to reduce, and they had a nitrate limit of about 10 milligrams per liter. With conventional process, they were actually achieving about 18 milligrams per liter. They tried the SND configuration, and they were able to reduce first the aeration demand about 42%, similar numbers that we obtained during the previous example. The SBI increased about 30%, but still was considered low. It wasn't considered bulk in sludge. And then, of course, then the F1, the overall F1 nitrate concentration reduced about 65%. So I've been talking about nitrate and nitrites and SND. So here I just have three case examples where, at least in my opinion, we can select for either SND or nitration or nitritation, denitritation. In this, for example, we just have a conventional facility, and this guy selected an MLE plant without primary clarifiers. Most likely by looking at the C to N ratio, the COD to nitrogen ratio required for SND, which is about 8. Most of the plants do have enough carbon to nitrogen ratio to achieve a high degree of SND. Therefore, in this case, it's most likely we're going to select SND via nitrate, just because we don't have a benefit or an energy benefit to go into nitritation, denitritation. I have here one of the recommendations I have is providing ammonia-based aeration control. And the reason to do so is to make sure that we can actually select, or we can select the aerobic SRT required for nitrification. And then, of course, it allows you to provide that. It's not the same as Live was saying, but it allows us very much to provide that DO within the range that you want to work with. And of course, in this case, we have lower energy generation potential since we're talking about energy. And the only reason why I say that is because in this case, we're just sending waste active air sludge to anaerobic digestions, therefore the energy potential is low. The second case I have here, it's in the similar plant than before, but now we have a primary clarifier. We know that primary clarifiers are really good removing, or fairly good removing carbon. Therefore, by doing so, most likely we're going to limit the C to N ratio needed for SND. In this case, you have to make the selection whether you want to go with conventional SND or nitrate shunt, and the decision will be made basically on C to N ratio, whether or not you have enough carbon to drive denitrification. And the last example I have here in cases where you have a two-sludge process similar to, for example, DC water or two other facilities being operated, the higher current plant here in Florida and Tampa. In that case, you have an A stage where we're actually consuming or reducing most of your carbon, and then when you go to your second stage, to your nutrient removal stage, you're actually carbon limited. In that case, it makes more sense to actually implement nitrate shunt since you don't have carbon to drive the denitrification. So, and we know that now we're looking at this configuration of nitrate shunt with a two-stage process. It's compatible with mainstream anomox, and that's kind of the research been going on these days, is to how to complement the mainstream anomox with nitrate shunt in a B-stage reactor. So my conclusion from these presentations are the following. We know that the application of S&D processes may be based on unlimited I. One, as we said before, we have to have carbon to drive denitrification or denitritation. Therefore, the C2N ratio is one of the most important parameters that we have to load when we looked at S&D processes. The sludge bulking is an issue, no doubt about it, but we have to be able to control it. And one of the ways we can control it is by using aeration-based control. Since the literature, at least that we've looked, doesn't show an indication that by doing aeration-based control, we actually encounter low DO bulking problems. Instrumentation and control requirements are going to be a little bit higher than conventional plants, but not much. So, and then the operators, of course, we know that we have a limited impact on some of the parameters that actually drive S&D. However, we're making strides into control in these processes now. Based on the results that we have from this presented here, we know that COD to nitrogen ratios of about 8, it's fairly adequate for S&D, and about 3 based on my experience for nitrate shown, based on the literature review and some of the batch experiments I've performed. The optimum bulk DO concentration it ranges between 0.2 and 0.7, so you can get both nitrification and denitrification occurring at the same time. S&D is more susceptible to nitrification limitations, and that's driven by the operating DO condition, and by denitrification limitation, but that's driven by carbon. And we can actually manipulate those two by controlling, especially the DO by ammonia-based control. We know that the advantage of cyclical aeration resulted, at least from the results that we have here, in a more ready availability of nitrite and nitrate generated during nitrification. Under constant DO concentrations, denitrification would rely on the slow diffusion of nitrite and nitrate from the outer nitrification zone to the flux into the inner nitrification zone to the flux. Therefore, we have to select that properly, and it's case specific. Nitrate shown, it's possible in mainstream facilities. However, it's going to be driven by the carbon to nitrogen ratio. And of course, we have to at least finalize or at least move forward our understanding into how we can accomplish this. I'm mentioning here transient anoxic, one way of doing it, but at least we're still trying to understand how that actually can be implemented in full-scale facilities. And with that, I think that's all we have for my first presentation.
Okay, thanks, Jose. Maybe just ask a couple quite a few people have asked questions related to kind of the COD to N ratio, and then also asking about HRT and SRT. So I don't know if you could kind of comment. They're not totally the same thing, but they're kind of related. But if you have a higher loaded system and maybe more aggressive on the design, that you end up having a shorter SRT, how does that factor into the ability to do S&D?
Well, when you look at an S&D facility, you have a couple of things going. First, you have to select the proper SRT to actually nitrify. And that's driven, and it's a little bit more susceptible in S&D facilities because of the lower DO. So that's one thing. But of course, by having a high rate system, and of course, and I think you mentioned as well HRT. In the case of HRT, the idea would be to provide just enough HRT so you can denitrify. You can use available carbon for denitrification without just because of the it's driven by that reaction as well, by the HRT. So you have those two components that you have to address, and they're similar to what we do right now when you design a post-anoxic zone. You look at the HRT and you look at the biomass available, and then you design your system in that way. In terms of the carbon availability, of course, even though we have two plots here, two examples where we're saying that C2N ratio is important, it looks that it's around 8. It will depend on several factors, and some of those are related to the HRT of the plant. In this case, we had fairly stable HRTs. We have about 6 hours HRT. So we know that the HRT was not a limitation. So as you go into more aggressive system and shorter HRTs, then that C/N ratio will play a major role, and you might need more carbon to drive within the flock to do the same process.
Okay, thanks for that answer. Another one I'll pitch out there is there have been a couple of questions on the old nitrous oxide. So could you comment on, operating at low DO, trying to get SND, what impact that will have on N2O, nitrous oxide emissions?
Well, when you actually operate at low DO and you go into the conventional nitrification, denitrification, there have been a lot of research that actually shown, and especially measuring N2O emission from oxidation ditches, that these reactors actually have lower nitrous oxide emissions than conventional nitrification, denitrification facilities, even though they're being operated at lower DO concentrations. However, if you go into the process of the nitration, of nitration, denitrification, there is a couple of good papers out there that actually show that by doing that, your nitrous oxide emissions is going to increase. Therefore, they're going to be higher than a conventional facility. That's the short answer.
Okay, thanks. There's several other questions, but I'll hold on to those and let you do the second presentation, Jose, if that's okay.
Yeah, that's okay. So the second presentation I have for today, it's changing a little bit of topic. I'm not talking too much about nutrient removal, but talking about a high-rate active air sludge system for carbon removal only. And that's the title of actually my presentation. The overview is going to be simple, and we have it here. I'm just going to talk about the evolution first of these high-rate active air sludge processes. Then some of the fundamentals and design considerations we have to actually understand before going into designing these processes. And then I'm going to talk about a case study, which is the Strauss wastewater treatment plant in Austria. First, I want to acknowledge my helpers, or at least my partners in crime. Dr. Charles Spott with HRSD, Mark Miller with Virginia Tech and HRSD as well, Hampton Roads Sanitation District, Dr. Sudhir Murthy with DC Water, and Dr. Bernard Wett with ARA Consults. We know that the high-rate active air sludge process for carbon removal, at least on my ability, was first developed, as far as I know, by Chase and Eddy in 1944. Here we have a copy of the paper that I found on the internet that actually talked about the development of that process. And it uses high food to microorganism ratios and low SRT with relatively short HRTs, hydraulic detention times, to remove organics from wastewater treatment plants. We know that the current application of these processes recognizes the following, that there are three forms of substrates in wastewater. One is particulate, colloidal, and soluble. We know that the particulate and colloidal substrate are actually removed effectively from solution by biological flocculation and also by absorption into the biological floc, and the subsequent, of course, solids-liquid separation. The soluble fraction can be removed three ways. One by intracellular storage, one by biosynthesis, and the other one by biological oxidation. As Leif mentioned previously, we know that 40 to 60% of the energy in a conventional active air sludge plant or in any wastewater treatment plant or aerobic wastewater treatment plant goes to the energy goes to aeration. So in the case of high-rate active air sludge process, it's more marked because we're not getting oxygen gains by doing denitrification in most cases. And the issue with aerobic treatment is that electrical energy is required to provide aeration so we can remove chemical energy. Of course, this practice is needed by current technology that limits carbon removal and to meet secondary standards. So far, when we talk about high-rate active air sludge, most of the time we're talking about high-rate active air sludge to meet an effluent requirement being discharged. They're most likely secondary effluent requirements. However, there are other applications that we're going to be talking here where where high-rate active rare sludge can be actually used to minimize or to maximize the energy recovery. We know that there are two ways, and that's our word you said, there are two ways of actually designing and operating high-rate active rare sludge. The first way is actually talking about carbon oxidation, which is normally the way that we design these high-rate active rare sludge systems. We just provide enough SRT with an adequate F2N ratio so we can remove the COD to meet a secondary standards. Normally, in those systems, we're talking about solids retention time or sludge age in the range of 3.5 days or a little bit less than 3.5 days. Food to microorganism ratios ranging from 0.5 to 1 grams per of BOD per gram of VSS. The fairly, let's say, long detention times ranging from about up to 3 hours. Of course, mixed liquors between 1,000 and 3,000 milligrams per liter and high DO concentrations, normally in the order of 2 milligrams per liter. The other way of operating this facility is by just optimizing the carbon absorption process, which actually will use less energy when operating these facilities. In this case, we're talking about systems operating at a really low SRT, lower than 0.5 days. Fairly high food to microorganism ratios, we're actually talking between 2 and 10 grams of BOD per gram of VSS. Fairly short detention times, less than half an hour, and DOs fairly low, normally in the order of less than 1, normally in the 0.5 milligrams per liter range. When these processes actually are using a similar configuration as we have here, which is a two sludge system, we can operate these facilities, high-rate active rare sludge plants, to minimize the ration energy needed to maximize the carbon absorption, which means we have to put just enough energy or air to gather or to capture enough COD or enough carbon so we can redirect that carbon to an anaerobic digester and make energy. And at the same time, we will reduce the load into the second stage, therefore to the B stage for nutrient removal, therefore less energy will be required in that stage as well. When operating, of course, in a two-stage process, we have the following. We know that we can operate at low enough SRT and low enough DO, so carbon oxidation should be minimized, which means pretty much all what we're doing, we're gathering or we're removing all the particulate and colloidal substrate or substrate by flocculation, which is a low energy process, and then we're storing some of the soluble COD into the floc rather than oxidizing it. And then the transfer of organic from the liquid train to the anaerobic digester is maximized. Therefore, more energy can be produced in this type of process. This plot actually was developed by Diego Rosso, and I stole it from him, and actually shows the process control variables affecting the COD removal in a high-rate active rare sludge process. That we know that to optimize the removal of carbon, we have three main variables or four main variables here. One is the SRT and HRT, which are sometimes coupled to each other. The other one is the dissolved oxygen concentration that we have to operate at, and then the temperature. First, I want to show this plot, which actually shows the effect of SRT, of the aerobic SRT on the waste active rare sludge volatile solids percentage. And this is important because we're talking about energy, and therefore what we want to do, first of all, when we look at high-rate processes, we want to maximize the amount of energy potential of carbon that we have in the wastewater and transfer that to the anaerobic digesters. In this case, as we increase the SRT of a process, we know that we get some assimilation, we get some actual digestion within the reactor, and then, of course, the VS content of the mixed liquor goes down. By operating at a shorter SRT, in this case about 0.5 days, we can actually maximize that VS percentage in the active rare sludge plant. Therefore, we will maximize the energy potential from that facility as well. By optimizing or to optimize these processes, we really have to understand the mechanisms involved in the removal of the substrate as a whole, especially the three types of substrates that we mentioned before: the soluble, the colloidal, and the particulate. And this plot actually shows the effect of the sludge detention time on the removal efficiency from a high rate active sludge process. As we can see, normally, as we said before, these high rate active sludge processes have been operated at fairly high SRTs, meaning 2 days or longer. And therefore, based on the results from these plots, we can see that everything there, the removal of the three parameters that were the three substrates have been maximized. So we're talking about getting pretty high removal efficiencies at the high SRT. However, as we start cutting down the SRT in the process to move more to a 0.5-day SRT, we can see that there is little effect on the SRT, at least in the SRTs we're looking at, on the removal efficiency for the soluble of the really biodegradable substrate. However, the colloidal and the particulate COD are fairly affected by just a reduction of the SRT. Therefore, we have to find a balance or where we want to operate this process to minimize actually the sludge shape, but at the same time maximize the removal efficiency to meet any requirements that you might have. When we talked about dissolved oxygen, we're talking about the operating dissolved oxygen in the reactor. And again, we have a similar plot to the previous one. We have the three substrates available in the wastewater. We have the really biodegradable soluble COD, the colloidal fraction, and the particulate fraction. And now we're looking at the effect of both the dissolved oxygen concentration on the removal efficiency for these three fractions. And again, we can see that by reducing the DO concentration, the first parameter that's going to be affected by doing such is going to be the colloidal fraction of the influent. Second, the particulate COD, and then finally the soluble COD. Therefore, by understanding these different parameters, these different effects of these parameters into the removal efficiency, we can actually select a good sweet spot to actually operate at low DO conditions, at a low SRT, but at the same time to maximize the removal rates of the process. In addition to do that, we also have to look at the way of minimizing, and as I said before, one way to operate the system is not only to reduce the SRT, but the overall goal of doing so is to actually promote the storage of the soluble COD substrate rather than the oxidation. We know that the oxidation of the soluble substrate will require higher energy requirements than just the storage, and that's what we wanted to show by doing these experiments. One thing that, and this plot shows the effect of the SRT on the specific aeration requirements per, and we have it here as SCFN per pound of soluble COD removed from a system. And we can see as we move closer and closer to the short SRT range, especially 0.5 days and less than 0.5 days, we can see a decrease in the actual specific aeration requirement to remove the soluble substrate from the reactor. At the lower SRTs, it looks like specific aeration requirement decreases, indicating possible carbon absorption and storage rather than oxidation. We still have to do more experiments to prove that and to actually understand a little bit more this effect. However, right now, based on the data that's been available and provided to us, it looks like by reducing the operating SRT, in this case, we can reduce aeration requirements as well. So by looking at just the different parameters that I've been talking about and how we can optimize the process control variables to remove COD in high-rate processes, we have this plot, and we have three arrows here, and I selected those arrows, one to represent particulate and colloidal removal, which is the flocculation process. One of the easiest way to actually maximize the energy potential from this type of process is by maximizing the removal of particulate and colloidal fractions of the COD, and therefore transferring those fractions from the aeration tank to the aerobic digester. However, at the same time, we have to try to find a sweet spot to operate at a low enough SRT and a low enough DO concentration to maximize the oxidation of soluble COD and to maximize the storage of the COD into the biofloc. And of course, and then we have the third arrow that talks about the volatile solids content of the waste active air sludge. And we know that by operating at a shorter SRT, we can actually maximize that VS content of the mixed liquor and therefore maximize the energy potential. Right now, especially Hampton Road and as well as DC Water, they're actually developing strategies to operate these A-stage processes, and they're doing so by actually tracking or measuring the carbon dioxide production rate from these processes. We know that based on the literature out there, we know that high heterotroph activity actually indicates that the carbon oxidation, which means if we have high production of carbon dioxide in your system, that could be related to the oxidation of the substrate in your process. By reducing, by the same token, by reducing that carbon production or carbon dioxide production, which means now that we're shifting from that that oxidation to the storage part of the process. Therefore, we're trying to understand a little bit more how we can use these new techniques to actually control high rate active air sludge processes. Now I'm going to talk about a case example. This data was provided to me by Dr. Bernard Wett, and this is actually the Strasse wastewater treatment plant in Austria. And it uses a two-sludge process, and it's an AB plant. It treats about the load varies from 90,000 to about 230,000 population equivalents. And here we have a flow diagram from the Strasse wastewater treatment plant. And right now I'm just going to focus on the A stage part of the process rather than the B stage or the size from treatment. Right now, of course, the A stage for this facility actually operates at an SRT of about 0.5 days. The HRT is roughly 30 minutes, and the DO concentration is about 0.5 milligrams per liter. The plot that we have here actually shows the COD mass balance for the for the whole plant, but I want to concentrate basically on the A stage part. We can see that the A stage part at the Strasse wastewater treatment plant removes about 60% of the COD from the incoming water, utilizing little energy. Of course, that COD is then transferred to the anaerobic digesters to maximize the energy potential. Some of the questions that we've had before doing this or looking at this data was to understand the actual energy potential of the waste active air sludge from the high rate active air sludge process compared to a B sludge to a longer SRT system, and that's what we have in this plot. Here we have in the upper figure we have the kind of pinkish and blue squares and diamonds. They show the gas production from digester experiments using A-stage sludge. And then the bottom plot, which has a triangle and the axis and the red line, shows actually the gas production, the gas production rates from the B sludge, the waste active air sludge from the B sludge facility. And of course, we can see that the tremendous difference between the two processes. Therefore, by maximizing the sludge production in the A stage, in the high rate active air sludge process, we will maximize the overall energy production rate of the plant as a whole. And of course, this data actually, it summarizes the energy. It's actually energy balance of the facility. And we can see here that fairly minimal aeration is actually required to operate these A-stage processes. About, I would say about 10% to 20% of the energy from the whole plant is just used to run the A-stage process. Therefore, however, it maximizes, it provides most of the waste active air sludge required to produce energy. So based on the conclusions we have here, we have to start thinking when we looked at high rate active air sludge processes, we have to start thinking about how we can maximize the energy generation potential of the systems rather than just throwing energy at it and hope for the best. We know that the energy or the carbon oxidation actually it's equal to the energy intensive system. The more oxidation we actually promote in an active rare sludge, the more energy we have to input into the process. However, by optimizing the process and by reducing the SRT and the DO concentration to some level, we know that we can convert these energy-intensive processes in a less energy-intensive by maximizing the absorption of the carbon rather than the oxidation. The proper selection of SRT, HRT, and DO is actually related to your effluent. It will be related to your effluent quality. However, the proper selection of these different parameters will maximize the energy potential of your facility. And the overall goal of the A-stage process, especially when you look at it and you try to implement an A-B stage process, is to transfer most of the organic from the liquid train to the anaerobic digester to maximize energy. That's my last slide for the second presentation.
Great, thanks, Jose. Got one specific question on your second presentation, and that was a question on dealing with filamentous bacteria. Obviously, when you're at these low sludge ages, that's one of the concerns of bulking sludge, so maybe you could talk to that a little bit.
Yeah, that's a real concern, and I didn't touch much about it during the second presentation. And based on the data that we have obtained, for example, at the Strauss wastewater treatment plant, we don't see sludge bulking or low DO filaments in the A-stage reactor. However, with the experience of some of the pilot plants being run in the United States, we are seeing some issues with sludge with low DO filaments, therefore excessive bulking. So it is of concern. However, it's a trade-off that you'll have to evaluate specific to your facility. So we have misinformation. We have in some cases, we do see some sludge bulking conditions, but the full-scale facilities being run in Europe don't see or we haven't seen any sludge bulking due to the low or the high rate system. Okay.
Thanks, Jose. That was the one specific to the second presentation. Maybe I'll just mention to everybody who's still on the webcast, we're kind of out of time now. We're going to continue, do a couple more questions, but for your CEUs, your PDHs, you don't need to stay on. If you're done, you need to get back to other things. Showing right now on the screen is a website, which is the FTP site that contains the slides from today's presentations. Also on there is a link to the form you need for your educational credits. So all that information is on that website shown there. So with that, I just got a couple more questions that came up. First of all, to you, Jose. There were a couple of questions focused on temperature effects for SND. Specifically, will it work at lower temperatures? And what are the impacts of that?
Well, based on observations that we had, most of the results that we presented on the slides in this presentation actually are from Florida plants. And therefore, the temperature, I would say the average temperature is about 20-25 degrees, which I wouldn't call low. However, there are many facilities being operated in SND mode in northern climates, especially in the northeast of the United States and also in Europe. For example, all of these A-B processes in Europe, especially, for example, Strauss, used to be on the second stage, used to run in SND mode, and pretty successfully even at the low temperatures. Of course, we know that the temperature will have a tremendous impact on your nitrification specifically. So you have to design properly, but we haven't found, besides the normal issues that we see with temperature and nitrification, we haven't found a marked effect to limit SND just to warmer climates.
Okay, thanks, Jose. I'll maybe pose this question to Life. Are you still there, Life? Did we lose you, Life?
Yeah, I hear you.
You're here. Okay. There were a couple of questions, both posted during your talk and then also Jose's, on the. Could you comment on the impact of running at a lower DO in terms of oxygen transfer? So the note from both was, if you operate at a lower DO, you'd require less air anyway. How much of an impact is that?
There's quite an impact, of course, because the efficiency is much higher at low DO concentrations because the driving force is higher, of course. So it's kind of a double win you have.
Cool. Now to you, Jose, there's another question on the A-stage aerobic process that was used for Strauss. Did they convert over from a primary treatment process? And then how did the energy change when they did that? So I think they've got a wrong assumption there, but could you kind of clarify on how Strauss came to have this AB process?
Well, maybe you know better than I do. So yeah, I don't know specifically if they converted from primary clarifiers to this AB process. However, some of the energy balances that I've done looking at this technology, of course, you can use primary clarifiers to reduce the organic loads into the B stage. However, you just have some limitations unless you want to add chemicals to it. But when you do the overall balance of primary clarifiers versus an A-stage process operated similar to what Strauss been operated, always in my experience, always the energy potential from the A stage is going to be higher, just because you put so little energy to remove most of not only of the particulate and colloidal fractions, but also the soluble, and you can transfer that, you can gather that and send it to the digesters for energy production. So always the A stage comes higher into energy production potential than the primary clarifier. But I don't know if the Strauss plant was actually converted from a primary clarifier to an AB process. Maybe some of you guys know, but I don't.
I don't know. I've always assumed that it was always an AB process, but I honestly don't know.
The way it's laid, it always seems to be that way, but I don't know.
Yeah. That's one for Bernard Vett next time we see him. I'll find him here and ask him that. I guess I've just got one last question for Life before we wrap up. There are a couple of questions on the basis for the cost savings that you've shown, the benefits that you've shown, and they wanted to know, is that in comparison to conventional DO control, say the DO of 2, or was it compared to no control?
I didn't mention that, yeah. No, it's clearly compared to normal DO control. So that was the standard we had. And so it's proper DO control at 2 milligram per liter compared to introducing ammonia-based control.
Okay, that's cool. And then there was a follow-on question that you showed one slide where by just moving the DO probe, it had an impact on your effluent ammonia, and they were wondering if the comparison that you did, if there was an energy benefit from moving that position of the DO probe, or how that was accounted for in the second study.
Of course, in this case, the main problem was to have sufficient oxygen. So it's not an energy saving. You will use more energy, but you make sure that you have a proper air distribution. Right. Yep. So you make sure that the DO probe location is right. So that's the first step. So you will see higher energy consumption, but better nitrification performance. And then the second step was to introduce ammonia control. And the advantage is that if you have high ammonia loads coming in, you have proper DO everywhere. So it's even improving nitrification then. So, and this is also much better than the concept they had before, where they realized that, well, most of the time we don't need high DO levels. So they reduced the DO set point in the last aeration zone to 1. Meaning if a peak comes in, you don't have full nitrification capacity. By introducing ammonia-based control, you make sure that you have full nitrification capacity if you need the capacity, and then you lower if you don't need it.
Okay, well, thank you both for some very good and thought-provoking presentations. Hopefully, it'll inspire folks to come to the conference in May. And thank you again for very good presentations and some good pointed questions and very good answers to all of them. So thank you, gentlemen, and thank you to everybody on the webinar for taking part, for listening. Thank you.
Thanks, Andy.
Thanks, Andy, for moderating.
Thanks. No